Hello to all, welcome to the channel Money's Gate Tech Vision. In this lecture, I will solve some of the GATE 2022 problems from the discipline of Electronics and Communication (EC) from the subject Network Analysis. This is the part 2 lecture series. In the part 1 lecture series, I have already solved two problems from the subject Network Analysis in 2022 year paper. This topic is also common for electrical, electronics and instrumentation. So all the students can view the lecture series. Let me move on to the problem. This is a problem number 3 from the subject network analysis. Already two problems I already solved in the previous lecture. You can go through that. So I will read out the problem. In a circuit, there is a series connection of an ideal resistor and ideal capacitor. The conduction current through the resistor is 2 sine t plus pi by 2. And the displacement current through the capacitor is dash. So here four options are given for the displacement current through the capacitor. So with this explanation itself, we can find out the circuit. The question is taken from the topic AC networks. So with the explanation itself, we can find out about the circuit. It is a series connection of resistor and capacitor. It is nothing but RC circuit. R and C are connected in series. Conduction current through the resistor is given us 2 sine t plus pi by 2. So since the resistance and capacitance are connected in series, we know about the series condition and parallel condition. So when the components are connected in series, current will be same. That we know. Voltage will be different. So here VR is a resistance across voltage across the resistance, and VC is a voltage across the capacitance. That will be different, but current will be same. With this itself, we can find out the answer. Answer will be the same. Since resistor and capacitor are connected in series in the given circuit, the current flowing through both the components will be same. So therefore, we can represent I equals IR equals IC. So IR is given as 2 sine t plus pi by 2. The same answer will be there. So same answer is given in option C. Option C will be the correct one. Hence, current through the capacitor is IC equal to 2 sine t plus pi by 2, which is given in option C. So this is one of the easiest problem. We can find out that. Let me move on to the next problem. Consider the circuit shown in the figure with input V of t in volts. The sinusoidal steady state current I of t flowing through the circuit is shown graphically, where tau is in seconds. The circuit element Z can be dash. Okay, here four options are given for Z. Whether we need to find out whether Z can be inductor or capacitor. Here one graphical plot is given. With the use of this plot, we need to find out the value of Z also. Okay. So this question is taken from the topic sinusoidal steady state analysis. Now we can analyze the question. So the question is given. The question is given here. So this circuit consists of the signal V of t equal to sine t. Sinusoidal waveform I of t is given. So in the graphical plot, I of t curve is given, and for I of t amplitude is given as 1 by root 2 amps. So here from the V of t signal itself, we can find out the amplitude as 1. So V of t equal to, it is nothing but sinusoidal waveform. It starts from 0 only. So with this itself, we can find out the waveform. The waveform will be like this. So waveform will be like this for voltage signal. Okay. Here time equal to pi by 4. Pi by 4 is nothing but delay. So here itself we can find out current waveform lags behind the voltage by pi by 4. Current waveform lags behind the voltage by pi by 4 by an angle. Okay. So this is the voltage waveform and this is the current waveform. So we can find out the about the current. Here the voltage V of t equal to Vm sin omega t commonly, and the current I of t equals to Im sin omega t minus theta. Theta is nothing but delay is given as pi by 4. So here itself we can find out the value of Z. So find out whether Z can be inductor or capacitor. For the inductor only, current lags behind the voltage. So from the circuit and graph, you can find out some of the values. In the circuit, V of t is given as sin t. From this we can find out the amplitude Vm equal to 1 volt and omega also 1 radian per second. And then what is current given? Im equal to 1 by root 2 amps. Amplitude of current waveform is 1 by root 2 amps and here minus 1 by root 2 amps. So we can represent Im equal to Im equal to 1 by root 2 amps. And then since the current lags behind the voltage, we can represent Z can be inductor. The given component Z can be inductor. Now, for the inductor also there are two options. In the option B, they have given us an inductor of 1 Henry and in the option D, they have given us an inductor of root 300. So here we need to find out the inductor value also. So let me find out the inductor value from the from the given graph already we have found out the amplitude of voltage and amplitude of current. To find the inductance value, we need to find out Z equivalent. Z equivalent is nothing but resistance plus JXL. So I am taking the modulus only. So modulus of Z equivalent equal to root of R square plus XL square. R is given as 1 ohms. XL we need to find out. XL is nothing but L omega. Omega is already given as 1 radian per second. So substituting R equal to 1 ohms and XL equal to L omega and omega equal to 1 radian per second in this Z equivalent. So modulus of Z equivalent will become root of 1 square plus L square omega square. When substituting when substituting omega equal to 1 radian per second, Z equivalent equal to root of 1 square plus L square. So this is one equation form. We can find out Z equivalent in other way from the value of maximum voltage and maximum current. So maximum voltage already we have found out, maximum current is given as 1 by root 2 amps. Maximum voltage V of t equal to Vm sin omega t already we have found out as 1 volt. Okay. So Z equivalent is nothing but RMS value of voltage by RMS value of current which is equal to Vm by Im. RMS value of voltage equal to Vm by root 2. RMS value of current is Im by root 2. So that root 2 and root 2 will get cancelled. And again it will be the ratio of maximum voltage and maximum current. So already we have found out from the waveform maximum voltage as 1 volt and maximum current as root 2, 1 by root 2 amps. So this ratio will become 1 by root 2 which is equal to root 2. Now I am substituting, I am equating this Z equivalent value in this equation. Okay, Z equivalent value in this side, in the left hand side. So Z equivalent equal to root 2 which is equal to root of 1 square plus L square. So taking the square root on both sides, 2 equal to 1 square plus L square which is L equal to 1 Henry. So we found out the value of inductance as 1 Henry. So option B will be the correct one. Option B will be the correct one. An inductor of 1 Henry. Inductor of 1 Henry. Okay. Let me move on to the next problem. This problem is taken from the topic two-port network. So I will read out the problem. A linear two-port network is shown in figure A. This is a two-port network given. An ideal DC voltage source of 10 volt is connected across port 1. Okay. And variable resistance R is connected across port. As R is varied, the measured voltage and current at port 2 is shown in figure B. So figure B is the graphical plot. V2 versus I2 plot. Note that for V2 equal to 5 volt, I2 equal to 0 milliamps. And V2 equal to 4 volt, I2 equal to 4 milliamps. That is in the negative axis. So minus 4 milliamps. When the variable resistance R at port 2 is replaced by the load shown in figure C, the current I2 is dash. So here on two-port network is given. In the input port, in the port 1, V1 is given and 10 volt is given, and in the port 2 at the output port across the terminals variable resistance is connected. So for this graphical plot is given. V2 versus I2 plot. I2 plot is I2 is given in the negative axis. So at 5 volt I2 equal to 0. At 4 volt at 4 volt, I2 equal to minus 4 milliamps. So this is the graphical plot representation. So what we need to find out? We need to find out the value of I2 when this variable resistance is replaced by this load condition, which is given in figure C. Okay. So what I am going to do is, I am going to apply the Thevenin's theorem. We can find out the voltage. See, I am taking the graphical plot first. From the graph, we have found out V2 equal to 5 volt at I2 equal to 0 milliamps. So I2 equal to 0 milliamps. So V2 equal to 5 volt at I2 equal to 0 milliamps. I2 equal to 0 milliamps is nothing but it is current at the output port will be equal to 0. If the current at the output port is 0 means it is nothing but output port is open circuited. It is meant for open circuit condition. Output port is open circuited, which the AB terminals are open circuited. AB terminals is open circuited means it is nothing but an open circuit voltage which can be represented as Thevenin's voltage equal to 5 volt. Okay, V2 equal to 5 volt. This 5 volt condition is nothing but Thevenin's voltage. I am going to apply the Thevenin's theorem. For the Thevenin's theorem, so what are the requirement? Thevenin's voltage and Thevenin's resistance. So from the graphical plot given in figure B itself, we have found out the Thevenin's voltage. Now we need to find out the Thevenin's resistance. For the Thevenin's resistance, we need to find out short circuit current. So what is a short circuit current? At the short circuit condition, that voltage should become 0. Here V2 starts from 5 volt, it is decreasing linearly up to 4 volt is given. Again it will be decreasing up to 0. So when it becomes 0, that we need to find out. That is the short circuit current. Okay. It should become, this should become linearly decreasing to 0. Okay. V2 should be decreasing. V2 is decreasing to 0 at some I2. That I2 is nothing but, that I2 value is nothing but short circuit current. Short circuit current. So we can find out short circuit current from the graphical plot itself. So given, what is the given graphical form? What is the given graphical form? So given graphical, in the given graphical form, we can find out the slope. So see here, what is the slope? Slope is nothing but y by x. So here, see here, what is y value? 1. And what is x value? Here 4 milliamps. It is in the negative axis. So 1 by minus 4. 1 by minus 4. So slope we can find out. 1 by minus 4. And with this slope, we can find out the short circuit current. Slope will be same in all the conditions. So short circuit current is nothing but at the short circuit current, V2 should become 0. Okay, V2 should become 0. That means that, this full value we can consider. Okay, this full value we can consider. This graph should be decreasing. It should become 0. Then full value will be equal to 5 volt. Full y will be equal to 5. So with the slope, where y equal to 5, x equal to short circuit current equal to dash. That we can find out for y equal to 5, and with the slope condition we can find out. So slope is nothing but y by x, which is already we have found out from the given plot, 1 by minus 4. So 5 by x equal to 1 by minus 4. We need to find out the x-axis value, x-axis length value. So here, hence x equal to 5 into minus 4 is nothing but minus 20 milliamps. That means at the condition of when it reaches minus 20 milliamps, the V2 becomes 0. V2 is decreasing linearly to 0 at I2 equal to minus 20 milliamps. This is the condition minus 20, and this is the condition minus 20 milliamps. At minus 20 milliamps, V2 will become 0. Okay. So this is the short circuit current. So we have found out the short circuit current from the given slope, from the slope condition. So with this short circuit current, we can find out the Thevenin's resistance also. So I am going to apply the Thevenin's theorem. I am going to connect this load instead of this variable resistance. So when the resistance R at port 2 is replaced by the given load shown in figure C, applying Thevenin's theorem to find I2. So when to apply the Thevenin's theorem, already we are having the Thevenin's voltage and short circuit current. With the use of this short circuit current and Thevenin's voltage, we can find out the Thevenin's resistance. So Thevenin's resistance is nothing but the ratio of Thevenin's voltage to the short circuit current. So Thevenin's voltage we have found out as 5 volt and short circuit current is 20 milliamps. So for the resistance, no need to consider the negative. So 5 by 20 milliamps, 5 by 20 is 1 by 4, that is 0.25, 0.25 into 10 power 3, 250 ohms. So we have found out the Thevenin's resistance. Now we can apply the Thevenin's theorem. So by applying Thevenin's theorem, VTH, Thevenin's voltage, we found out as 5 volt and Thevenin's resistance we found out as 250 ohms in series with the load. So figure C is connected across the terminals AB. Now we need to find out the I2 value for this circuit, for this closed loop circuit. So we can find out easily. What is I2? V by R. As per Ohm's law, V by R. So here total voltage, 2 voltage source is given, 10 volt and Thevenin's voltage is 5 volt. So 10 minus 5 by total resistance is 1000 plus 250. So hence I2 equal to 5 by 1000 and 250. So this will get cancelled. 25, 1 by 250. So 1 by 250 is nothing but 4 milliamps, 0.004 amps. That is a 4 milliamps. 4 milliamps in the opposite direction. So no need to consider the negative sign. So I2 equal to 4 milliamps only. So hence the answer is 4 milliamps. Okay. So this is the analysis of the question paper. This is Mani's Gate Tech Vision. This is a channel for engineering competitive examinations. You can view the lecture series. You can subscribe to my channel and you can view the lecture series regularly. Thank you very much for watching the video.